Hello. Uh, Today, uh, uh, in second lecture, I will continue the first lecture. At first lecture, I discussed the derivative concept. Okay, and I gave the definition of derivatives, which is y prime equal to f prime of x, which is a limiting concept of a ratio of two changes, delta y by delta x, and delta x tends to 0, of course. And this is mathematical notation of the derivative is dy by dx. Okay, dy by dx. And we saw that this mathematical term has different interpretations. Geometrically, this is tangent line problems, okay, standard line problems, or finding slopes, okay. And physically, this is rate of change function. Okay, how to find rate of change function? Okay, so, and economic theme of derivative is marginal concept, which is in fact per unit something. Okay, marginal cost, marginal revenue, marginal product, marginal profit, marginal utility. This is per unit something. Okay, and it has its humanistic approach. Okay, that is how sensitive is one variable. Okay, and or how sensitive is one, how responsive is one variable to another variable. That is how that is sensible. Okay, so now I will give you a very exciting real life example. And nowadays the hot issue is COVID-19 situation overall the world. Okay, and I have data. Yesterday I collected this data from WHO. Okay, you can see a table. Okay, first column is week of March and April. That is here is data of for 7 weeks. Okay, we can see, and second column is infected cases. Okay, every week in 1,000 people. Okay, and second column is infection rate. Okay, data is weekly. You can see that for first week in March, infected people was 6.5 thousand people. Okay, and with compared to previous week, it was 67% infection rate. Okay, second week, this was 12.5 thousand infected people. Okay, and then third week 23,000, then fourth week 38, and then 48. Okay, and in first April, this is 48.7 thousand, almost 49,000, and then 36,000. Okay, 36,000 in second week. Okay, second week 36,000, and third week of April is 27,000. Okay, we can see. But if we see, compare the first week, second week, third week. Okay, um, 6, 6, 12, 23, 38. This is with compared to these first, second, and third weeks, we can see that the second and third week of April. Okay, this increasing number of people. Okay, infected increasing. Okay, second week ছিল মার্চে 12,000, সেকেন্ড উইকে এপ্রিলে আমার 36,000, থার্ড উইকে 23, এখানে 27,000. সো মনে হচ্ছে যেখানে আমার সিচুয়েশন কি ওরসেনিং, ইয়েস, ওকে, খারাপ হচ্ছে সিচুয়েশন। বাট আসলে আমরা অ্যাবসলিউট ভলিউমে, অ্যাবসলিউট কোয়ান্টিটিতে কোনো কিছু দেখে আসলে কম্পেয়ার করতে পারবো না। সিচুয়েশন আমরা যদি দেখি ইনফেকশন রেট, সেক্ষেত্রে আমরা টোটালি উল্টো চিত্র দেখতে পাবো। উই ক্যান সি যে ফার্স্ট উইকে মার্চের 67% ছিল ইনফেকশন রেট, সেকেন্ড উইকে 91%, থার্ড উইকে 85%। অনেক কী বলে হাই ইনফেকশন রেট ছিল। ওকে, বাট আমরা যদি কম্পেয়ার করি এপ্রিলে, আমরা দেখতে পাচ্ছি যে ফার্স্ট উইকে 26%, যেটা কিন্তু অনেক কম ইনফেকশন রেট। হ্যাঁ, অ্যান্ড সেকেন্ড উইকে -25%, ইভেন ইনফেকশন রেট এখানে নেগেটিভ, দ্যাট ইজ কি ডিক্রিজিং। হ্যাঁ, অ্যান্ড থার্ড উইকেও আমরা দেখতে পাচ্ছি -25%। সো আসলে ইনফেকশন রেট যদি আমরা দেখি, অ্যান্ড দ্যাট কেস কম্পেয়ার করতে আমাদের অনেক সুবিধা হচ্ছে, এবং আমরা দেখতে পাচ্ছি যে আমাদের মার্চের যে ইনফেকশন রেট ছিল সেটা আসলে এপ্রিলের চেয়ে অনেক হাই। এপ্রিলে আমাদের ইনফেকশন রেটটা কি আমাদের ডিক্রিজ করছে। সো সিচুয়েশন গেটিং বেটার। সো আমরা দেখতে পাচ্ছি যেটা অ্যাবসলিউট ভলিউম আমরা যদি দেখি সেক্ষেত্রে টোটালি কিন্তু উল্টো ছিল। সো ইউ ক্যান সি হাউ ইম্পর্টেন্ট ইজ ইন রেট অফ চেঞ্জ ফাংশন, দ্যাট ইজ হুইচ ইজ ইনফ্যাক্ট কি ম্যাথমেটিক্যালি দিস ইজ ডেরিভেটিভ অর rate of change, okay, or whatever we say, slopes, no? So so if given a COVID function in absolute quantity y equal to c of t, so in that case we can find infection rate by differentiating the c of t function with respect to t, and we will get dy by dt, which is in fact c prime of t, okay. So this is in fact differentiation problem, okay. But for integration, in advance I would say that in integration in fact আমাদের রিভার্স সিচুয়েশন, ওকে। সো গিভেনই থাকছে আমাদের রেট অফ চেঞ্জ ফাংশন, ইনফেকশন রেট ফাংশন, অ্যান্ড টু গেট দ্য কোভিড ইনফেক্টেড function, COVID infection function, the original function, সেটা we will integrate the rate of infection rate function, and we will get the c of t function, that is which is in fact the original COVID function, okay. So this is the case. Okay, now I would like to focus on roots and uh, uh, discovery of calculus, okay. Calculus rooted in fact the ancient by the ancient Greek mathematicians Archimedes, okay. He calculated areas of triangles, rectangles, squares, circles, even volume of pyramids, okay. This type of shapes, okay, they calculated in fact, but modern calculus which starts its journey by discovering the fundamental principles of calculus in fact at the second half of 17th century, okay, with the discovery of limiting concept and continuity concept, okay. But over 18th century, in fact this very crucial mathematical part, okay, mathematics was in fact undiscovered. Four major mathematical problems, okay, were undiscovered over 18th century. In fact, significant development did not help, okay. We can see what were the problems. This is tangent line problems or slopes problems, that is how to find tangent lines or slopes of a general curve, okay. And again, how to find area of a general region, or how to find length of a general curve, and how to find volume of a general solid. The ancient mathematicians did not know how to calculate these measurements, okay. And how to find maximum or minimum of a quantity, and they didn't know also how to find velocity function or acceleration function from a given position function or distance formula. And conversely, they did not know also how to find position function if given velocity, and how to find velocity or acceleration function if given position function, okay, or converse, okay. You understand, I think. Fundamental relationship between two problems discovered by Newton and Leibniz. This is a differentiation problem, okay, differentiation problem and integration problem. What were the problems in fact? It is they connected two problems, two types of problems. In fact, we can say that these different types of problems is can be interpreted in mathematically, geometrically, physically. Okay, so geometrically this was tangent lines or slopes problem for differentiation, and for integration this is area or area function problems. Physically this is how to find instant rate of change function, and for integration this is how to find original function in absolute quantity, and mathematically this was how to find derivative function, and for integration this was how to find antiderivative function. So in fact three pairs of problems, in fact one problem, just different interpretation. Okay, mathematical, physical, geometrical. So we have to understand this basic concept. Okay, and for differentiation, in fact, what is given for differentiation? Given always original function. Okay, original function y equal to f of x, original function, and our task is to find how to find rate of change function. Rate of change function, that is we differentiate, okay, the original function. And for integration is reverse process. Given, in fact, a rate of change function y equal to small f of x, here also f of x, small f of x, but this is original function, this is rate of change function. And question is for integration, find the original function. Okay, and that is capital F of x, so which is antiderivative function. So we are in fact we have to integrate the rate of change function. We get antiderivative function, which is capital F of x. Okay, capital F of x, both this one. Okay, so rate of change function here given, we integrate by find capital F of x. So we can see that the fundamental relationships between differentiation and integration is to connect two types of problems. Yes, that is derivative function and antiderivative function. Okay, or geometrically this is tangent line or slopes problem to area function, or physically this is rate of change function to original function. Okay, and by differentiation we get from original function to rate of change function, and by integration we get from rate of change function a original function or antiderivative function. But thank you, but whatever I wanted to say, this is all. Okay, thank you.